And oops, and I will now share my screen. Okay, thank you very much. Yeah, so I'm Carol Francis Glover, and I'm from the Center for Electrochemical Science and Engineering, or CEASE, here at the University of Virginia. And as Marta said, my talk is the many colors of metal-rich primers, corrosion protection mechanisms, and latest developments. And I'd really like to thank the Eurocorr organizers for inviting me to give this talk. Very sad that we can't be there in person, but it's great that we were able to still do this virtually. So here's a picture of the most kind of famous or prominent building here at the University of Virginia, which is in Charlottesville on the East Coast. This is the rotunda, and the solitary figure you can see there is very representative of how things have been around here since about March. So there we go. So the contents of my talk today, I'm going to introduce the motivation and challenges for the development of metal-rich primers. But I'm predominantly going to focus on magnesium-rich primers today. And then I'll talk through the requirements for a viable sacrificial anode, because I want to demonstrate the work that we're doing here at University of Virginia to actually come up with some new, novel, non-toxic sacrificial alloys, which can ultimately be used as magnesium-rich sacrificial primers. So the bulk of the talk will be on a sort of case study focusing on magnesium tin alloys for the protection of another magnesium alloy, which is AZ31B. So that will include how we go about screening for a new sacrificial anode and the protection performance of a candidate sacrificial anode. And then I'll summarize with the next steps and challenges involved with actually incorporating that into a full coating system. So the motivation for developing metal-rich primers, or magnesium-rich primers in this case, derives from the fact that we have this worldwide drive to replace chromate. So over in Europe there, we have EU REACH legislation, and here in the US, surprisingly, with the political climate at the moment and things changing all the time, there is actually a lot of legislation on the federal level and on the state level to, in many cases, just reduce the amount of chromate that's being used. But the sort of desirable scenario, a desirable solution for that is to just replace it entirely so that we're not having to work even with small amounts of it, given that it's the impact on the environment and human health. Okay, so here in the US military has actually over the last sort of 10 to 15 years spent a lot of time and resources studying magnesium-rich primers. For many years, zinc-rich primers have been successful in protecting steel. Magnesium is a great option for the protection of aluminium, magnesium alloys, and galvanized steel, where we've got a zinc layer. But the military has been slow to adopt magnesium-rich primers for use on its DoD aircraft fleet, because there are still questions surrounding the exact reasons that protection is afforded. And there are a few things that are uncertain in terms of the long-term protection. When we already have chromate, which obviously has its environmental issues, knowing that it's going to keep things protected is actually the #1 priority. But some of the things that are of concern are the effects of hydrogen embrittlement. So if we have a driving force that's too large in terms of the sacrificial anode relative to the substrate, we can then have the detrimental effect of hydrogen evolution, which can then embrittle the substrate. The unknown effects of the chemical conversion of metal pigments as it's used up. There's a lot of research that suggests that this is actually a positive, that we can get this deposition and form a secondary barrier if we have a scratch or a defect that exposes the substrate. But because it's not fully known, you know, what happens as the coating uses up, that's another concern and another challenge. There's the effect of the performance of the metal-rich or magnesium-rich primer in terms of incorporation into a full coating system. So if we have a top coat in place, or a pre-treatment of any kind, like a conversion coating, is that sacrificial coating just going to become redundant if it can't make electrical contact with the surface, or if it's being blocked by the top coat? And finally, how long will it last in service? That's a question that is unique to every different magnesium-rich primer or any metal-rich primer. Is it going to just be used up? It may be effective, but will that last for a short period of time? So these are all challenges and reasons why magnesium-rich primers haven't been fully adopted. And the DoD out here in the US is a major driving force for the development of these kind of coatings. And actually, some of the work that we're doing now is has been and is sponsored by the Army Research Labs. So I want to talk about the work that we do here at UVA in terms of taking into consideration those challenges and coming up with new magnesium alloys, which could ultimately be turned into pigments that are incorporated into magnesium-rich primers. And there are two requirements for a viable sacrificial anode, which need to be there are essential requirements, which when we're screening these alloys, we can't sort of be confident that these will be satisfied, then we know that we can reject those options. So the first is that we need a negative couple potential. So the galvanic couple potential of the substrate when coupled to our sacrificial alloy must remain consistently lower than that of the open circuit potential of the substrate for extended periods of time. What we, as I mentioned on the list on the last slide, one concern is this hydrogen evolution, which can occur if we're too negative in terms of our sacrificial anode. So getting somewhere close to the substrate is ideal, but what we don't want is potentials of if this is the potential of the substrate and this is the potential of our sacrificial anode, we don't want a situation where this is too close and we have the potential for detrimental polarity reversal. And the schematic on the right there shows that, where actually if that becomes the case, we're in a really bad situation, because the coating, which is supposed to be protecting the substrate, it's actually going to drive corrosion. So we really want to avoid that. So that's the first one, a negative couple potential. And the second one is, and my screen doesn't seem to be, there we go. Hopefully it'll stay there. And the second one is that we want low self-corrosion of the sacrificial alloy itself. So two things there. We want to maximize the cathodic polarization on the protected metal, and we want to minimize any residual anodic reaction on that sacrificial anode. So we want to make sure that all the current coming from that sacrificial anode is going towards protecting the surface and not on it just corroding itself faster. We want that sacrificial anode to last as long as possible. So minimizing that self-corrosion is really important. And so what we're really looking for is hitting a sweet spot between the two, because as with anything, it's never easy, and the two things aren't exactly complementary, especially when we're talking about magnesium, which is very negative in potential, so it's an excellent candidate for the protection of substrates like aluminium and other magnesium alloys, but it suffers from extremely poor corrosion performance, and that is largely due to this phenomenon of anodically enhanced cathodic activation, which in brief is where regions of prior anodic activity provide a surface of enhanced cathodic activity. So it's kind of a self-perpetuating, cathodically driven mechanism, where magnesium surfaces that have already undergone anodic attack gain an extremely high intrinsic exchange current density for the hydrogen evolution reaction. And what we end up with is something like in the image shown there, where we get an entire surface very quickly covered in this layer of dark filament-like corrosion product. So for many years, various research groups around the world have looked at ways that we can protect magnesium from corrosion, because if alloyed correctly, it can be strong enough to be incorporated as components in terms of aerospace and automotive industries. And one way is to provide coatings for magnesium. And sorry, the other thing I wanted to say is that because it's lighter than aluminium, so if we can include it, then we are, you know, for aircraft in particular, it's lowering fuel consumption and making things easier. But it seems to be the key way, rather than just relying on a coating, is to actually alloy the magnesium with something that can poison that hydrogen evolution reaction. And groups from Monash University and Swansea University showed back in 2012 that additions of arsenic can actually poison the hydrogen recombination reaction and greatly slow down the overall corrosion rate. However, when the goal is to, in terms of coatings or anything in terms of materials, when the goal is to replace something that's toxic and carcinogenic, it's not a good idea to replace it with something else that is toxic. So it's great that it shows that it can be done, but arsenic is not the answer. So the same groups, and also actually Professor John Scully from here at the University of Virginia, had a look at group 14 and 15 elements to see if any of those would work in the same way, but could we find something that was not toxic. And tin was one of the candidates that showed some good results. And researchers from the Korea Institute of Material Science and the University of Science and Technology in Daejeon, also in Korea, characterized magnesium tin alloys after they'd been immersed in a salt solution. And they found that there were reduced hydrogen evolution rates. And this was put down to a tin-enriched surface layer that was accumulating at the interface between the passive film and the underlying alloy. And so this tin-rich layer was able to act as a surface for sluggish hydrogen evolution reaction kinetics, which coupled with the magnesium matrix and effectively replaced the sites for this strong hydrogen evolution reaction on the normal magnesium hydroxide corrosion product. So tin seems to be an ideal candidate in terms of a non-toxic alternative to arsenic. And I'm just trying to change my slide again here. It's being a bit slow. I'll just continue talking until that catches up. Come on. Okay, there we go. So that brings me on to the bulk of this talk, which is discussing how we screen for a new sacrificial anode using the magnesium tin candidate as an example, where we're looking at the protection of magnesium alloy AZ31B. So we wanted to determine the performance of 3 different compositions of magnesium tin alloys. So we looked at 1, 5, and 10%. The really nice thing here is that tin is soluble in magnesium, so we didn't have any second phases to worry about. And what we were really trying to work out was what's the optimum composition based on the three that we have available here that can provide continuous sacrificial protection with the lowest corrosion rate. And is there a sweet spot where, or a kind of a compromise where we have both of those things going on at once? So first was the study of candidate alloys individually to screen in terms of the two requirements that I mentioned for a viable sacrificial anode. And the second was to study candidate alloys in situ when actually coupled to the substrate. So the first thing, and probably the easiest test that any corrosion scientist might do when they want to study something, was to simply measure the open circuit potential of the candidate alloys and also the AZ31B, which would be our substrate. So we did this in 0.6 moles sodium chloride over 24 hours. And I should mention that this work was done with a previous PhD student here at UVA, Dr. Taylor Kane, who now works at the Army Research Labs. So this is the first step, which gives us a lot of information about whether protection may or may not be afforded by these candidate sacrificial alloys. And the good news is that the line at the top, the most positive potential over, or predominantly most positive potential over the 24 hours, belongs to the AZ31B. So that's what we want to see. And all the others on the whole remained more negative, i.e. sacrificial, more anodic, and seemingly able to provide protection. However, for the higher tin loading, there were a few areas of concern in the first sort of 5 hours, and then for the magnesium 5 tin later on around 17 or 18 hours, where it's a little bit too close there, and we run the risk of polarity reversal. But at the lowest tin content, the magnesium 1 tin, the open circuit potential remained lower than the AZ31B for the entire period. So that was kind of the most positive result there. The other two were a little bit iffy. So the next step was to, or in the next phase that I will discuss, we will look at them in situ and see how they perform. But first I want to introduce an electrochemical scanning technique, which is something that I used extensively when I did my engineering doctorate back in Swansea University, and which I still use now at the University of Virginia, which is the scanning vibrating electrode technique, or SVET. So I'll give a brief explanation of this so that you understand what's going on. So we take samples of roughly, they can be up to 3 by 3 centimeters, but all this is, all the work I'll present is roughly a centimeter squared kind of size. It's an immersion technique, so it's fully immersed in salt solution, and we have a platinum probe which vibrates in the solution above the surface and rasters in a sort of map or a profile in solution. And the platinum tip is, here at UVA anyway, the one that we use is approximately 50 microns in diameter. And it doesn't touch the surface at all, so there's no sort of detrimental effect from the experiment. And what the SVET actually measures is the difference in potential between the lowest and highest points of vibration, giving us the peak-to-peak voltage, which can be converted into the vertical component of the local current density. So these potential differences in the solution arise ohmically because of the ionic current flow that's generated by the local corrosion cells that are going on the surface. So we use the equation given on the slide there to convert to the vertical component of current density. And we have there the kappa is solution conductivity, so it's different for any solution that we use. And then the peak-to-peak amplitude is the APP. So that's the SVET. And hopefully a few things will become more clear now with this slide on which just demonstrates the corrosion over a 64-minute period of high purity magnesium. So this is the control. This is work that's been done previously by the researchers at Swansea University, but one that I've replicated here, which very neatly demonstrates anodically enhanced cathodic activation. So with the SVET, we get these maps, and we map regularly over whatever time period we like, an hour up to multiple days if you want. And it gives us these snapshots of what's going on in terms of the anodic and cathodic activity on the surface. So it gives us the intensity and location. And something else that we can pull from this data, which you'll see later on, is we can integrate the positive and negative corrosion activity and then plot for each map as a function of time to give us an idea of the corrosion rate. But what we can see here is for high purity magnesium, we have anodic regions, which is shown as the peaks in red, and then cathodic regions, which are the troughs in blue. So we have anodic activity occurring around the edges to begin with, and over the 64-minute period, these sweep inwards across the surface, and the entire surface is just left with this black corrosion product in a very short space of time. But the really interesting thing to note here is that in the wake of these anodic occurrences, we're left, as I described earlier, with this intense cathodic region, which remains, if you look at the 64-minute part, you know, an hour earlier, this region was anodic, and after that entire time, that surface is now intensely cathodic. So it's that cathodic reaction that drives forward the corrosion. So that's the scenario for high purity magnesium. What happens now when we incorporate tin at the lowest percentages? This is 1% tin. And the first thing to note is that the experiment was now conducted over 9 hours instead of 64 minutes, which is a really good sign. So compared to the pure magnesium, we've really slowed down the progress of that cathodic activation, but it's still very much there. We still have a wall of anodic activity, and we still have cathodic activity that spreads right across the surface and doesn't switch off in that entire time. But it is greatly reduced, so that's positive. When we come to the magnesium 5 tin, we have a much different scenario now where I've just shown snapshots that were within an hour of each other. Again, the experiment was run for 9, or actually I think it was 10 hours in total. And as you can see by the picture, once we've removed the sample from the solution, the whole surface hasn't been covered. And what we saw was these individual anodes rather than this wall of anodic activity. And the cathodic activation this time in pre-corroded regions, which would be here at the bottom of this map here at 7.8 hours. We know this is pre-corroded because we can see the anodes here. But this time that cathodic activity is switched off and is shown only directly behind that local anode. So that's a good sign again. It seems that with the more tin that we introduce, the less corrosion we're getting. And finally, if we look at the magnesium 10 tin, this is reduced again. And SVET now can't detect the cathodic activation. It doesn't mean that it's not there, but the resolution isn't high enough for it to be detected. So this time we also didn't observe this movement of the anodes. They kind of just appeared and disappeared in a kind of like a kind of whack-a-mole game, unlike the other tin loadings. So as I mentioned, we can integrate the anodic and cathodic activity. And here, if we look just at, so the two should be equal and opposite. So I'm just displaying the anodic current densities here over time. And this very neatly shows us that, so we can semi-quantify the fact that as we increase the amount of tin, our current density decreases. Okay, so just to quickly summarize, in terms of assessing individual alloys there, the magnesium-1 tin is shown to be consistently more negative than the AZ31B substrate. It does improve in terms of cathodic activation relative to the high purity version, but it definitely had the most severe anodically enhanced cathodic activation out of the three compositions. Both magnesium 5 and 10 tin were inconsistently more negative than the AZ31B substrate, which is cause for concern, but both displayed very good corrosion properties in terms of reducing that enhanced cathodic activation. So now I want to go on to the assessment of the protection performance when we're actually in situ with that AZ31B. So this time the experiments were run in the exact same way, but I took the each magnesium tin candidate sacrificial alloy and I electrically connected it to a piece of AZ31B, and they were mounted and polished so we had a flat surface. And this time I was scanning across the interface of the two metals. So in each case I'll show maps in the same way, where the AZ31B is on the left and the candidate magnesium tin alloy is on the right. And what we're looking for is the scenario like the one shown here, where the AZ31B remains blue, i.e. cathodic for the entire 24-hour period in this case, and the magnesium tin remains slightly red. So that would be the ideal scenario if we could just see that for an extended period. But of course, it's never that simple. And here's an example of what happened with the magnesium-1 tins, the lowest concentration. The good news is that the AZ31B was protected for the entire time. So that's a very good starting point. However, beyond this first hour of immersion, we saw this very intense corrosion activity occurring on the magnesium-1 tin. So not all that current was going towards protection. There was a lot of self-corrosion and cathodic activation going on there. If I move to the, if I move to the magnesium-5 tin, things started out really badly for the first 10 hours. So right from the start, the AZ31B was anodic, and the magnesium-5 tin was having a free ride, being protected for that time. However, the good news here is after about 10 hours, for the remaining 14 hours, we had polarity reversal in the right way, so that protection was afforded for the second half. And the corrosion on the magnesium, or the self-corrosion on the magnesium-5 tin, was pretty minimal. So if we ignore those first 10 hours, which obviously we can't do, but if we just look at the sort of remaining time, that's kind of where we want to be for our ideal sacrificial alloy. And finally, I'll go on to the magnesium-10 tin, which was just bad news from 75 minutes on. In fact, the first 75 minutes were perfect, and then beyond that, we just had severe corrosion. We had polarity reversal and then severe corrosion on the AZ31B. And just quickly, that's the images of the three substrates. So the AZ31B has this kind of grey tarnished look, but actually was protected for the whole time. Whereas we can see this localized corrosion on the surfaces that were coupled to the magnesium-5 and 10 tin. So I want to finish by just going through the semi-quantification of what we just looked at and show you how it's really good in terms of working out exactly, or quantifying exactly how much current was going towards protection and how much was going selfishly towards corroding the candidate alloy itself. So we can split the two halves and look at the anodic and cathodic current densities, integrated anodic and current densities on each side. So if we look first of all at the magnesium 1 tin, so the solid triangles in the middle here show the anodic activity occurring on the substrate, and it's great, it's at 0, that's exactly what we want. And then here we have the anodic contribution from the magnesium 1 tin. And by actually looking, because we know that the anodic and cathodic should be equal and opposite, if we look at the cathodic, we can see that, so this was the contribution. If we think of the anodic in terms of the magnesium 1 tin, this was our contribution of current that went towards protecting that substrate. And this was the extra that went towards the self-corrosion. So what we want to do, this part is fine. This part is what we really, the cathodic on the magnesium 1 tin, this is what we really want to aim to reduce. So I'm going over now, I'm going to just skip through. I'll briefly just mention that, actually probably this one shows it best. So this was the first 80 minutes of the magnesium 10 tin coupled to AZ31B example. And this gives us the dream scenario where all of that cathodic current from the AZ31B is going towards protecting is going towards protecting the anodic. Sorry, I'm messing this up. We have low anodic current on the AZ31B, and all the anodic current on the magnesium 10 tin is going towards protecting it rather than self-corrosion. So we can work out the charge by doing current multiplied by time. So we can look at the total charge over the 24-hour period. So we can again quantify, sorry, I'm looking at the wrong screen there. We can then quantify how much charge occurred on the AZ31B. So for magnesium 1 tin, it's nice and low. It's very high for magnesium 10 tin, which didn't go so well. But if we actually look at the charge from the 11-hour point onwards on the magnesium 5 tin, this is our first 10 hours, which were not good. But if we look at this, we can see that that's kind of a good sign there. Which brings me to concluding our findings here, which suggest that our sweet spot lies somewhere between 1% and 5%. Where we're avoiding that polarity reversal, which really is first and foremost the thing we need to get right in terms of a candidate sacrificial alloy, but then minimizing that self-corrosion as much as possible. So that will be the next step to try to home in on those compositions. So I'll just finish off here with a couple of slides. So the next steps, once we've actually optimized the alloy composition, we then want to convert that alloy into metal pigment, into a powder, incorporate it into a primer, an organic primer, optimize the pigment loading, and then optimize in terms of application methods. So in the lab, that might be spin coating, but ultimately we probably want to spray coat and make sure we can get the desirable thickness. And then we have a whole new set of challenges once we are able to apply that coating. So we want to look at that in terms of top coats and pre-treatments to see whether we can still get the right electrical connection. And these can all be done in the same way as the experiments that I showed here, particularly the SFET is great for testing coatings in this way. So I'm going to finish there and just acknowledge some of my sponsors and funding. So over the last year, I was really lucky to receive the Phil Parrish Fellowship in Engineering here at the University of Virginia. And then the US Air Force Academy as part of the Corrosion University Pilot Program, NSF, the National Science Foundation, and then for the coming year, the Army Research Office, or ARL, Army Research Labs, are supporting the research. So thank you very much. I will stop there and come out of, okay.
Thank you very much, Carol, for this interesting talk, showing very many results in this hot topic, and also for pointing out important challenges for the future. Actually, we strongly agree to answer some questions from the audience in case we have them. Let me have them. There is no questions right now. Maybe somebody will start. If not, just to remind the audience that the authors, in this case, Carol, you can contact them through the attendance list in the virtual Eurocorr. Okay, now we have one. But people can't hear me.
Oh, it's better. So
It's better?
yeah.
Okay, we'll close it. I will go closer to
Oh,
yeah.
No worries.
So, Basili, if there is any question, Carol can answer that. If not, you can contact her through the attendance list in the Eurocorr. Okay, now we have one. How were the two metals electrically bonded during the SVET testing? Interesting.
How are they electrically connected? Yeah, so the really important thing there, or the thing that was kind of difficult to get right, was making sure that we didn't have any crevice corrosion going on between the two. So it was definitely a case of trial and error. But so they were literally just put together and then connected on the back with wires coming out and then mounted in epoxy. But that had to be really well tested to make sure that the two were connected without any gap at all, because then you're just going to have a different form of corrosion going on, which is a problem.
Okay, great. So it seems that that was the only one. I just remind you that you can contact the authors through the attendance list. And yeah, people are saying congrats for your talk. And another one, do you plan to make longer exposure times, several days or even months?
Yeah, so the plan is, in terms of the testing the sacrificial bulk alloys, 24 hours, because we're in a pretty harsh environment, if it's able to survive that, we can then test for longer. But ultimately what we want to do is look at atmospheric corrosion as well. So once we've turned these alloys into powders, we'd then be coating panels and then doing salt spray kind of tests as well for much longer periods of time. But this seems to be, I think if it can survive 24 hours in this environment, is a good sign just for the screening process.
Okay, thank you so much, Carol, again, and thank you also for the audience to join us today in this fair lecture. And just we hope you to carry on with your successful career, and I hope to see you all tomorrow in the virtual Eurocorr again.
Thank you.
Thank you.